Now let's talk about line integrals. Now I think line integrals should be appropriately called path integrals. I think that's what some people call it. But path integrals are usually used for a completely different type of integrals that's used in physics. It's very, very hard. So I think most textbooks just say line integrals. But this is misleading a little bit because what you're trying to do is you're not trying to integrate over lines, but some kind of curves. Okay? So let's think about the following case. Let's say you have some function of x and y, and you have some kind of a curve C. Now, usually in multivariable calculus, when you're given a curve, you want to describe it by the parametrization of the curve, right? So you use this RT, which is the position function of a moving particle that's moving on this curve, right? So if it begins from here and ends there, at each time t, the particle is at some point here, right? And the particle's x position is given by this function x of t, and the y position is given by this function y of t, with t being between a to b. In such a case, we can talk about the integral of this function over the curve C times ds. Okay, what is ds? ds is the following. If you have a curve, and if you divide this into many, many, many small parts, this very tiny part of it is what we call ds. Okay, so it's a small length element. That's what it is. Okay? And what we're trying to do is, I'm trying to multiply the function to this length element, and I want to add it up as we go along the C. Now, when do we need to calculate something like this? Well, physically, sorry, I guess it's a storm, right? Okay, physically, this is the case when we have a density, a linear kind of density, on a small wire. So imagine this is a wire. Let's say this is a wire, and it's not uniform density. So some parts are more dense, some parts are heavier than the others. Okay. So if you have the density described by this function, then because this is a linear density, when you multiply it by the length, you get the mass of that part. Okay, so this gives you the mass of this very small part, and if I add them up, what would you get? You get the mass of the entire wire. So that's when you have to calculate such an integral. Now the geometrical meaning of this is, since fx comma y equal to z gives you some surface over this three-dimensional space, what we're doing is we're basically finding the surface area captured between this curve until you hit this surface. So there's this surface that's perpendicular to this surface that I have here, right? So that surface area of the thing captured between the graph and over this curve is this quantity. Still, another case when we want to calculate this is when you calculate 1 ds. Now, what quantity would this give us? I mean, if f is just 1, if it's a constant value of 1, if we calculate this, what kind of quantity would we get?
Scalar.
I mean, it's some scalar, but what's the meaning of that scalar?
Density.
Is it the area? Like an area or line?
What is ds again?
Density.
No, fxy was the density.
Oh.
What's ds again?
Small.
Small segment, length of that small segment, right? Okay. And we add them up. What will we get? The length of the whole wire. Okay, this will give you the length of the whole wire. It'll give you the length of the curve. Okay. So these are the cases when we would want to calculate such a line integral. And as I said, although we say it's a line integral, it's really done over a curve. So it's like a curve integral. How do you integrate a function over a curve? So this is how you write down the integral. Now I still have to explain to you how this is done. And let me, rather than trying to explain that abstractly, let me try to explain this by using a concrete example. Okay? All right. So let's say your function xy, x comma y is like 3x squared plus 2y. And let's say your RT is 4t comma 2t minus 1.
Wait, I'm sorry, can you explain what RT is again?
RT is the parametrization of this curve. I mean, if you have RT, you remember how we use RT to describe curves in space? Yeah, that's what this is. And let's say t goes from 0 to 2. So this is how our curve is described. What's the shape of this curve? Do you think you can figure out? It's linear, exactly, right? Because this is power of 1, right? So if you plug in 0, you see that it starts at 0 comma negative 1. So your y-intercept is negative 1. And your slope, when x moves 4 steps, y would move 2 steps. So the rise is 2, whereas run is 4. So rise over run, 2 over 4, you're going to get 1/2 as the slope. So if you actually drew this, you're going to get the line that's like this. Slope 1/2, like that. And t goes from 0 to 2. What does that mean? T is 0, that means x is 0, and t is 2, that means x is 8. So it's from 0 through 8. So that's what we call our curve as. Okay? From here to there. And the amazing thing is, see, this is not the only way to parameterize this given curve, right? We know that, right? There are many different parameterization for the same curve because, I mean, you can make the particle start from here and go there, or you can make the particle start from here and come back that way, or you can make it go fast and then slow. You can make it go really quick, or you can make it go slow. There are millions of different ways to parameterize the same thing. Okay? Now, if you want to see just one other parameterization of the same thing, let me give you an example. Here's another parameterization. RT is 2t, t minus 1, with t being 0 to 2. If you think about the graph of this parameterization, it's exactly the same curve C. Okay. You can try out different values of t and you'll see that they give you the same exact curve. Okay. Now, if you start at the wrong end, then you might get the opposite value. So actually, C is something we call as a directed curve. It's not just a curve. When we talk about line integrals, they're actually directed curves. Direction matters because if you go to the opposite direction, then they get the opposite integral value. Okay. All right. But coming back, So now let's try to compute this integral. What is the function integrated over this curve C? How would we do this? Now here's how you think about it. ds is the norm of dr. What is r? Well, r is the position vector. So r is the positions, and dr means it's a vector obtained by change of positions. So dr is this vector. You know, if you have point A and point B, and if you do B minus A, you get terminal minus initial. That gives you this vector from A to B, right? It's the same thing. If I have 2 points and if you subtract, you get dr, which is a vector. It's a vector quantity from a point to another point. And if you take the size of that vector, the length of this vector is what we call the small length element, right? So that's the relationship between the two. And then if we divide both sides by dt, we get the following identity, that ds dt is the norm of dr dt. And what is dr dt? This is r. dr dt means I differentiate this by t, so what do I get?
4, 2.
And what's that? And therefore, ds is 2 radical 5 dt. If I solve this, ds over dt equals to 2 radical 5, I can rewrite it as ds equals to 2 radical 5 dt. Let's continue the calculation here. So here's what I achieved. I figured out that if you were to do fxy ds over the c, you can rewrite ds as 2 times radical 5 times dt. Now that's a good start, because I don't know how to handle s, but I know what dt means. T varies from 0 to 2, right? So now I can say it's from 0 to 2. Okay? Then what? What's fx comma y? That's fx comma y, right?
Yeah.
Now, however, there's one more thing to think about. See, as you're multiplying this times ds and you're adding it along the curve C, what you're doing is this function f of x comma y is evaluated on each point of C. See, on this curve C, at each point x comma y, I'm taking this value and plugging into fx comma y to evaluate this, right? So I can't just use this. This x and y has to be substituted with the points on this curve. How can we do that?
Talking about ds over t.
This is the x-coordinate of the curve. This is the y-coordinate of a point in the curve, right? So for each value of t, this and this are x and y values. So that's what I do. I plug in this, and then if I compute, that's how you do the integral. Okay, let's pull the 2 radical 5 outside because that's a constant multiple. 4 squared is 16. 16 times 3 is 48, so you have 48t squared plus 4t minus 2 dt. If we integrate, this is 16t cubed plus 2t squared minus 2t. And I have to plug in 2 and 0. If I plug in 2, that's 128 plus 8, that's 136. No, yeah, 136 minus 132 times 2, so it's 264 radical 5. So that's what you get. I just did this quickly because that's something that you all know. But I just wanted you to see that x and y has to be replaced by x and y coordinates of RT. That's how you compute. Okay?